Hi everyone! Our objective of this lesson is to really wrap up all the terms that make up our first unit. So getting right into it, on the first side of your sheet, we have the point on the line segment that divides into two segments of equal length is known as, that point is the midpoint. Our midpoint here could either be H or C. So we're going to figure out what the lengths of these are. So I'm going to use my GeoGebra tool. I'm going to click right here on FH. And I'm going to find our value, and from F to H it's 4. The only way H can be our midpoint is if H to G is also 4. So when I check that out here, our value says it's 6. It can't be a midpoint. So trying the same thing out for our ACB line segment, when I click here, I'm going to make sure that my value, so right now it's hovering over the entire piece, that's 6. So if I venture off and move this to make sure I'm highlighting the right one, and I take that value, it's 3. So this line segment is broken up into two pieces by a midpoint. So C is our midpoint in this case. We can indicate that by making a little dash mark just to recognize it, but we'll get further into that in our lesson tomorrow. So moving our way down the page, we have a blank can be a line, ray, or a segment that passes through the midpoint of another segment. In our blank there, we're going to write in the words segment bisector. So a segment bisector is going to be something that cuts one segment in half. So in this case, in this example, we're given two segments. We have the segment AB and we have the segment DE, and they intersect here at C. So we want to figure out if either of them are segment bisectors, which means the same thing, that C would be the midpoint. So in order to see if C actually is our midpoint, at least for one of these segments, we're going to need to know if they are bisected, if they're cut in half. So for the first one, when I look at AC, I'm going to click, and actually I'll first get the whole thing here of AB. So when I get the value of that, it's 8. And I can move that just so it's a little bit out of my way. But when I click here, I'm just going to switch to the other segment that's lying here. So my AC value, when I get that value, it's 4. So if the whole segment is 8 and this piece is 4, that would mean BC is also 4. So we can say C is the midpoint of AB. We can also say that DE bisects AB. So for part A, it does bisect. And we can say AC equals 4, BC equals 4. They're cut in half. The entire thing, AB equals 8. So we can write that out as part A. For part B, we have to be careful. Just because DE bisected AB doesn't necessarily mean that DE will be bisected by AB in the reverse fashion. Remember that geometry is very particular about how it's worded, so we want to read carefully. So AB bisects DE. Well, if I look at this whole thing, DE, I get a value of 8.29. So we can see just by me drawing out this segment bisector here, you can tell that realistically this is not going to be at the midpoint. C cannot cut DE in half in this case. Yes, there is a situation like if I were to make this smaller, and I'm just going to go here and get my value of this other line here. But so if I have 2.75, I could eventually bring it so that way we would have a segment bisector of both pieces. The only time this would be relevant though is if it's stated that they were bisecting each other, that both pieces like A, B, and DE were bisectors of each other. In this case, we don't have a picture like that. We have one that was more stretched out. So as soon as you see those values not matching up, that's how we know that DE is not cut in half evenly, C is not the midpoint of DE. So AB does not bisect DE. So there is one situation where it will, this is not the case. So for that notice part, be careful. Notice language matters. If they bisected each other, that's when we would have 4 different congruent pieces going on. Moving on to our next new term, we're looking at the angle DAB. So similar to a segment bisector, we can also have angle bisectors. So that's what AG is in this case. So an angle bisector can be a line, a segment, a ray that divides an angle into two congruent angles. So we're going to have angles with two congruent measures. So when I take a look at that, if I look at my angle here, A or GAD rather, I get 30 degrees there. So I know right in between this is my 30-degree angle. If I do the same thing for angle BAG, we again get 30, so we know it's been cut in half. We have 30 and 30, and if we really wanted to go one step further, we could, and we could measure out BAD. And we see that 60 pop up. So an angle bisector is the same as a segment bisector, only for an angle. And finally, our last vocab term here is any two line segments or rays that intersect to form strictly a 90-degree angle or right angles are said to be perpendicular. And we can say, for example, that AB is perpendicular to CD. That's the symbol on your notes with the two lines meeting. But anytime you have perpendicular lines, you'll have 90. And we should know, because angles on a line here add up to 180, that we would also get 90 over in this angle, AEC. We'd also have 90 here at AED, and angle DEB as well. They would all have 90 degrees going around. So flipping our lesson over, we're going to talk about properties of lines. We've already introduced lines as infinitely long and straight and thin, but we're going to draw scenarios to kind of explain the properties they have. So the first one, through any 2 points, only one straight line can be drawn. So that's to say, if I have a point A and a point B here, if I want to draw a line, notice I can't ever not touch this line. So with that, there can only be one line that hits both of those points. Moving into part B, the shortest distance between any 2 points is the line segment. So in this case, when I look to connect 2 points again, if I look at a segment here, one point to the other, there's no more direct path than right here. Yes, we have the 4.22. It could be longer depending on how far away your points are. It could be shorter depending on how close they are, but it's never going to have a better path than right to it. So that straight path is always going to be your best bet. So again, the shortest distance between 2 points is the segment that connects them. For part C, when we look at two different lines will either share, intersect, blank, or blank, known as parallel lines. Any two lines that share 2 or more points are the same line, so two different lines will either share 1 point or no points. If they share 2 or more, then they're same line. So basically, if I look at that picture, and I have a point A, or just a point here, and I make a line. So any line that goes through that, if they share this point, it's only going to hit one time. So notice anywhere I go, there's only one intersection for those two lines. Unless they have multiple points and it becomes the same line, which means they'd have infinitely many points. Okay? If instead I don't have any points in common, so drawing in another line here, the only way that could happen is if they're parallel. So they'll have no points. You'll see if I click that, I could zoom in, I could zoom out. They're still not going to touch. But as soon as that point moves, even a slight amount, eventually you'll see they'll hit somewhere. It might not be visible at first, but somewhere they're going to touch. So those two different lines can either intersect at 1 or no points. And last one, so I'm just going to delete this out so we don't have this blocking our view. We could have, through any point not on a given line, there's exactly one line that can be drawn to be parallel. So if I have a point here and I have a line underneath, there's only one exact point that can go through this point as a line that won't touch. So we'll see that line. So if I touch that point, here is my parallel line. So again, I could zoom in, I could zoom out. They're not going to touch until they get too close together, then we won't be able to tell anymore. But the second that I try to move that, second that I try to move my line, even a hair, eventually it will touch. So there's only one possible parallel line, and that's known as Euclid's parallel postulate, and we'll talk more about that as we get closer to proofs. But for that, that's our first exercise. The second exercise, we're going to do the same idea, but we're going to break it down for a little bit different. So for the first one of exercise 2, we have through any point on a given line, there's exactly one line that can be drawn perpendicular to the given line. So again, if I start with a line here, just 2 points, once I've created that line, if I try to make a perpendicular line, I can see from angles before, we know that perpendicular lines always create right angles. So if I try to make a perpendicular line here, I would notice, I'll put in this 90-degree mark so I get it exact, and if I draw a point through that line here, so if I go for the line here, there's only one possible. There's 90 on all these sides, but the second I try to play with this, I won't even be able to move it because, you'll see that it won't be aligned with our 90-degree anymore. So the only one that works is just one perpendicular line. Through any point not on a given line, exactly one line can be drawn perpendicular to that. So we'll see, just like we did before when we had parallel, we have one point, and if we have a line that extends here, there's only going to be one possible line that makes 90 degrees. That's why I can even select this given angle, and you'll see here that if I go 90 degrees, it's only going to be on this exact line. Okay, there's no other place for there to be 90 degrees. And we'll talk about the half planes in class tomorrow. So we'll talk that further, but other than that, I will see you all tomorrow. Have a great night.